Okay, so in this video we're going to solve problem number 39 and also problem number I think 68 that you guys had trouble with in the class. Okay, so here's a quick solution to 39. What's happening in 39 is that there's a plank, a board of length L that is sliding to the right with speed v. Now, right when it enters, but when it starts sliding with speed v, it enters a region where the coefficient of friction is mu k. Now before this everything is frictionless, so it's going to slide, and then the first question is find the acceleration as a function of the position x, where x is the amount of the length of the plank that's on the surface, and then we have to also find the speed, initial speed v, given that the plank stops once the entire plank is on the surface. So to answer the first part, here's what we're going to do. So first let's look at the surface again. This is the part which has friction and a certain portion of the plank. Let's say a portion x of the plank is on the surface. Okay, now you haven't been given the mass of the plank, but let's just assume that the total mass of the plank is m. So total mass is equal to m. Now if the total mass is m, then the mass per unit length, which we'll refer to as lambda, mass per unit length, okay, equals lambda is equal to the total mass divided by the length. Now once we have this, what we can do is we can figure out the mass of the portion that is on the surface. Okay, so mass on the rough surface is equal to lambda times x, which is nothing but m over L times x. Okay, now that we have this, what we can do is figure out the contact force for this mass and then the force of friction on this mass. So the force of friction for this mass is going to be equal to the force of contact times mu k. So it will be mu k multiplied by the force of contact for this mass, so m over L times x. Okay, now once we have this, then what we understand is that, sorry, m over L x times g, there's a g missing there. So this is the force that is pointing to the left, and as a result the acceleration, okay, is going to be equal to simply mu k m over L x g divided by the total mass of the plank. Okay, understand that the force is only acting over a portion of length x, and the acceleration is for the entire body. So the acceleration is the net force divided by the mass, which is precisely what we have here, and this ends up being equal to mu k times g over L multiplied by x, and all this is pointing to the left. It is slowing it down, so it will have a negative sign in our equation. Alright, so this is part A of the problem. And part B, it says with what speed is the block moving such that it stops when the entire length is on the surface. Okay, so here we're going to apply the work kinetic energy theorem. We know W equals KEF minus KEI. So for this, we'll find the work done by this force of friction, and then once we have the work done by the force of friction, we know the final kinetic is 0 and the initial is what we're looking for. Now, since the force of friction is changing, the work done is going to be equal to F friction times dx, and we'll have to go from 0 to L, and this will be equal to 0 minus 1/2 times m times v square. Understand that capital M is not given, so we need to make sure that it is eliminated. Alright, so 0 to L integral, and then the force of friction is equal to, we'll do have a negative sign there, minus mu k times g over L times x, and there is also a capital M, and all this multiplied by dx, and this is equal to minus 1/2 m v square. Alright, now you can factor pull all the terms out of the integral, the constant terms, minus mu k x L, and then I have x dx equals negative 1/2 m v square. The m and the m cancels out, the integral simplifies to, so the negative sign also actually goes away, you can just leave it here, minus mu k g, and this becomes equal to x square over 2, 0 to L, and this is equal to minus 1/2 mv square. Now if we simplify this, what we realize is that the negatives go away. I get minus mu k, the halves, the 2 also cancels on the denominator, and then the integral simply becomes equal to this, and this tells me that v is equal to square root of mu k times g times L. Alright, so that's the answer to that question.